Hello, welcome back, friends. We are still working on the test number 4 review. This time, looking at number 18. Says in a study of the effectiveness of diet on weight loss, 20 people were randomly selected to participate in a diet program for 30 days. We are testing a claim that the diet had no bearing on weight loss. Use this level of significance 0.02. And we are assuming that the distribution is normally distributed just so that we can carry out this little statement. Distribution is normally distributed. This is one of the requirements for a t-test. And of course, we are doing a t-test because it looks like we're going to be talking about something to do with the average weight. This one is the weight before the program versus the weight after the program. It gives us, this appears we can only guess based on the context that these 20 pairs of data values, for example, the 178 and the 182, I'm sure that these are from the same person, right? Because we measure their weight before the program, we measure their weight after the program, and that leads us to believe that this is a matched pairs sort of a sample because it's a person matched against themselves. So what we are dealing with here actually is that situation where we are just going to look at the difference, the average difference. So if we make the mean be like mean 1 minus mean 2, where this one is the mean or the weight before and this one is the weight after, then what we will have actually is going to be the mean here. What I'm trying to state is that we are going to need to, first of all, go into stat edit. We need to pull up our tables over here, and we need to do the thing that we did before, where we're going to put list 1 with the before weights. We can put list 2 with the after weights, and then list 3 we can make it be the difference. And then we will look at those differences and tell if the average, by the way, if there is the null hypothesis can be that there is no difference because we're checking whether the diet had a bearing on their weight loss. So did the diet make a difference or not? So we're checking whether the difference is 0. So their weight before and their weight after, the difference should be 0. That means that they lost no weight, they gained no weight. And then the alternative hypothesis will just be that the difference is not equal to 0, because maybe looking at this program, I see a few of them where the person gained some weight. So it's possible that this diet is such a crummy diet that people are actually gaining weight on this one. Like maybe they're doing the nutter butter peanut butter sandwich cookie diet where that's all that you eat is nutter butter peanut butter sandwich cookies or something like this. I've heard of these kinds of ridiculous diets where it's really just somebody who has given up on their own health. But we are going to carry on entering this data. So we will start with the before the program weights. And so I'm just going across the row, entering these in to the best of my ability, trying to be accurate, but also not spend too long because this is a pretty hefty data set, 20, a sample size of 20, which really is a pretty small sample. That must be why they had to put in that little remark about the population being normally distributed, because otherwise a sample size of 20 is not that much. So I got list 1 in there, and then the weight after the program, these will be all lined up with the corresponding weights before the program, because like I said, these must be the weights of the actual person that we measured before. Now we're measuring them again after the same person with a matched pair kind of style. So we want them to be all lined up. That way when we take the difference, we are measuring the weight loss of each particular individual. And then, another 203. We are almost there. We got all 20 of them. And now into list 3, we'll go up and highlight list 3 and press enter. Now we're going to be able to put in a formula for them. We want to do list 1 minus list 2. We want to subtract these entries. Wait, what happened? What did I do with my formula? I'm going to clear that one out and try it again. It didn't seem to work too well. I'm looking for list 1. Do I have it there? Minus list 2 equals, it worked this time. I don't know what I did before. But there we have it. List 3 is all of those differences. And so now we're going to check by means of a t-test. We will go to stat tests. We're doing a t-test because it is a mean. We're checking the mean, so we need t-test. And we're able to do a t-test as just one sample. We're considering this as one sample because we're only checking those differences. And we actually have data this time. We don't have the stats. We don't know the mean and stuff. We have the data there. We're checking whether the average is equal to 0, the average difference. That's coming from list 3. We're checking whether it's not equal. We're ready to go. And we have, let's see, a p-value of 0.163, which that's greater than the level of significance of 0.02. So we will fail to reject this one, which when we fail to reject, we're saying that there's no difference. Whether you did the diet or not, you may gain weight, you may lose weight, but in general, your weight's not going to be any different and probably will just be the same afterwards. So we can say something, and I don't really have space to write it, but if you're under the sound of my voice, you can receive the conclusion verbally. It will state, of course, and since we're used to doing these by now, it should be familiar with you. We will say something like, there is not sufficient evidence to conclude that the diet had any bearing on weight loss. We would like to use the context from the problem to make that conclusion. And we could, of course, refer something about the level of significance. We can bolster that statement as much as we want, but I think that that's pretty much sufficient, as long as we understand that we will fail to reject this null hypothesis because there was not enough evidence. And then we are going to also look at number 21. This will be a very nice one. It just gives us some stats over here. We're testing a hypothesis that these two means are the same. Now, since it gives us these different stats, like this one for population 1 and population 2, and notice they have a different size. Population 1 has 50 in there, population 2 has 60, so there's no way we're going to be able to match these up or that they were chosen dependently. This is the one where they were independent, so we're looking for something like a 2-sample because that's what we're dealing with. And since it's a mean, of course, mean goes with the t, so we're looking for, isn't there such a button as a 2-sample t-test, or else it's 2-sample? You know, some of these things you just have to look in the menu and see what is available. But by the way, yeah, it's randomly selected. By the way, it just wants to let us know that we are able to use a t-test. Even though it doesn't tell us the size of the population or anything, we just have to assume that it matches all the requirements. And then we have a level of significance like 0.05. So this will come into play. Now we're looking for, oh, there it is, 2-sample t-test. That's what we're looking for. And then we have stats this time. The first sample goes, there's 31 out of, oh, and we actually need standard deviation. Is this one, the SX1? It goes 1.5. It tells us that one, but it calls it in the problem S1. N1 should be the sample size 50. X2 bar 29. The second standard deviation goes 1.9, and then this size was 60. We're testing the hypothesis of whether they're equal. So the alternative hypothesis must be just that they're not equal. We don't really have anything to go off of that it should be less or greater. We're just looking for not equals. That will be the alternative to equals. Now we can calculate this one. Oh, wow. Look at that p-value. It's so small. It goes, c times 10 to the negative 8th. So it goes And then 1, 2, 3, 4, 5, 6, 7 zeros in a row, and then goes 1, 2, 4. So this is the p-value. That's the probability to get such a thing if they are actually equal. And what, because you can see, this proportion is much more than this one. What is the level of significance? This is, is much less. This is less than the level of significance, which is 0.05. So we would reject this, and these means rather, not the proportions. I don't know what in the world is the point of talking about the mean necessarily, because there's no context. It's so funny to do these problems with no context. The mean of what? We don't know what this mean is referring to, but we will just blindly do this test, and we will attempt to come up with an appropriate conclusion. For sure, our null hypothesis, we're testing this one. Oops, I don't mean to put an equals there. Should be a colon like this one. Whether these two means are the same. This one is whether the two means are different. And so I was getting mixed up. I was not imagining that there's a bar here, and I thought that this is somehow a proportion. So whatever I said about proportion earlier, ignore that one. This does not have to do with proportions. It has to do with means. And so probably there's 50 bags of M&Ms. We're checking how many of them are brown or something. This one, or rather 50 M&Ms in a bag, 31 of them are brown. Or if there's 60 M&Ms in a bag. No, because I'm still talking about proportion. What am I going on about? Guys, help me out here. I'm making mistakes. But it's going to be okay. This is a mean. Do we need context to talk about the mean? Here goes the sample size. And this is the mean of something. So we take a sample and we're measuring the mean. But what kind of variable can have a value like 31? I know a ruler has a length of 30 centimeters. So is there something that can be around a foot long? I wonder. Maybe we went to a carnival and we purchased 50 hot dogs that are supposed to be foot-long hot dogs, and we measured their length in centimeters. The average length was 31 for these 50 hot dogs. And then we went to a different carnival in the other state, and we bought 60 hot dogs, and we measured their length. They're also supposed to be foot-long hot dogs, but they had an average of 29 centimeters. And so this state must not be Texas, because they're too small, these hot dogs. They're not really a foot long. But there is a bit of a variation. These hot dogs, they must be homemade or something, because there's no factory made these hot dogs. They're too variable, I guess. But whatever. We're going to carry on by saying, oh, by the way, the alternative hypothesis should have been that the means just are not the same. They don't have the same average length. And we have decided, based on this p-value, that we should reject the null hypothesis. So we would say there is sufficient evidence to conclude that the means are different for these populations, for population 1 and population 2. Of course, all the context about the hot dogs and so forth, I hope it's helpful, but it's all made up. We would like to include some of that context in here, and I don't mean to be all jammed up with my work there. There's the conclusion, if you can read it. That's number 21. Please let me know if there are any more questions about this one, and I hope you all have a wonderful day.